Hello CIO class, and welcome to another installment of Chemical Engineering Design. In this lecture we will cover the concept of internal force convection. So in this lecture we first briefly discuss velocity and temperature profiles again, revisit the concept of flow regimes, which we have already been over before, very much in piping systems design, but it also is very important for heat transfer, and then also determine the hydrodynamic and thermal entry lengths of pipes, which obviously relates to things like the resistance coefficients, which we were introduced to when we have pipe entrances and exits for piping system design. We'll also analyze heating and cooling for fluids based on two cases of constant surface temperatures. So you can think of these as coming about when you have latent heat of evaporation or condensation, so like at the top of a distillation column or at a reboiler, and also constant surface heat flux. Okay, so if there's a constant rate of heat flux, then we tend to use other equations depending on the application. We'll also consider pressure drops, which we have now become quite used to in piping system design, as well as friction factors, and also the Nusselt number for cases of fully developed laminar flow, as well as turbulent flow, of course. Now consider a fluid that is stationary inside a vessel as shown. We call this fluid irrotational. It's not really moving much. As soon as it approaches or is close to the pipe entrance, the negligible velocity begins to increase. So as this fluid begins to flow through the pipe entrance, it develops a velocity. Now this leads to the onset of a velocity profile inside the pipeline, which develops more and more and eventually becomes a fully developed flow at some distance inside the pipe. The region where the flow is still developing is referred to as the hydrodynamic entrance. And the fully developed flow regime obviously will follow after the hydrodynamic region. Once we have fully developed flow established, it is quite easy to determine things like the average velocity, the Reynolds number, as well as other things like the convective heat transfer coefficient, the Nusselt number, fluid properties, etc. So we like fully developed flow, and as chemical engineers, we tend to have very long pipelines where these flows will be established as fully developed. Okay, but nonetheless, we also want to take cognizance that we could have developing flow regimes as well. Okay, so for the case of the average velocity for the fluid, we can use the conservation of mass law to determine this. And it comprises the following integral for the cross-sectional area, as shown here, where the velocity boundary is taken from the wall to the center of the pipe. So obviously we integrate then from r equal to 0 and then r equal to capital R. Now since the density is constant for an incompressible fluid, we can rewrite the equation as follows. Okay, so we take rho over, and then we can also consider the following relation where the cross-sectional area changes with a change in the radius. As we integrate the radius, obviously we integrate for the cross-sectional area. But since the cross-sectional area itself is a constant, we can obviously arrange the equation again, and then we end up with an expression where we integrate for the average velocity between the two boundaries, where the average velocity is simply the average between the Vmin, which is taken as 0 because of the no slip condition at the wall, and the Vmax, which is obviously at the center of the pipeline. And we have seen this before. We know that the average velocity is simply these two velocities added together and divided by 2. Now, what of the thermal boundary layer? What does this look like exactly? Of course, there would also exist a developing region, and we refer to this developing region as the thermal entrance region of the pipe or of the flow through the pipe. And this is followed consecutively by a fully developed flow region, as shown here in the red. The following equation is used to describe the average thermal boundary temperature for the fully developed region. I won't get into the derivation. It's not necessary for this course. The following equation we all know all too well. Okay, so this is a recap on what we have already covered. And first off, we know that below certain Reynolds numbers of 2300, flow is laminar. Flow is then transitional and then turbulent based on, this is from the textbook, one of the textbooks, but for piping systems design, we tend to look at transitional flow as between 2300 and 4000, and anything above 4000 you will definitely have turbulent flow. You can also have laminar flow past these Reynolds numbers up to, I think they've measured it up to 10,000 Reynolds number, and this is when you really have no surface roughness at all. You can get laminar flow at very high Reynolds number, but those cases are really rare. We tend to have these sort of cutoffs, and my recommendation to you is rather follow the recommendation in the piping system textbook rather than the heat transfer textbook. Where you work with heat transfer, use the heat transfer textbook. Anything regarding piping system design, rather use the piping system design handbook. Right, but what you would not be familiar with is that there exist different forms of the Reynolds number depending on the geometry of the pipe. The change comes in the form of what is known as the hydraulic diameter. So for the case of cylinders, the hydraulic diameter is simply the diameter of the pipe in question. For square and rectangular geometries, the following equations are used instead to determine the appropriate hydraulic diameter to use with the Reynolds number when calculating it. And obviously the Reynolds number is qualitative. We don't report it with decimal places. If you do so, I will probably just mark you incorrect for that entire question, because that's common sense. It's irrational to give decimal places. Understand the Reynolds number and its use. It is a qualitative value. It does come into play when you have to calculate Nusselt number, for example. But when you want to determine flow regime, stick to whole numbers, integers, etc. Okay. We should also be familiar with the use of resistance coefficients, Kr, for pipe entrances and exits. But how do we determine the entry lengths that these resistances are associated with before flow actually becomes fully developed? Because a lot of the equations we are using, we assume fully developed flow through long pipes. We have two sets of equations that we can use for determining the hydrodynamic and thermal entry lengths depending on the flow regime. So when we determine the length of pipe required for a heat exchanger, for example, we then need to go and check again to see, do we in fact have fully developed flow? Is it a significant portion of the pipe? How much of the length of that pipe is taken up by a hydrodynamic entry length or a thermal entry length? Okay. And as a quick exercise before we move on, quickly pause here, try to determine these entry lengths for the following cases yourself, and then move on to check your answers. So if you've completed the exercise, did you or were you able to obtain the following results? If you were not able to, just try again, quickly pause, and just practice. All right. So at this point in the module, we are very close to now being able to design heat exchange equipment, but we will still need a bit more equations to perform such designs more accurately. Now, when using the Newton's law of cooling, for instance, we have often just made use of the average temperature. However, when dealing with heat exchange systems, if you do the integration across a length of pipe for heat exchanger, it is sometimes more appropriate to make use of the following relation, which you get from that exercise, that mathematical derivation. What you end up with is what is called the log mean temperature difference. Okay, so you can prove this mathematically to yourself that this is the case. This is an equation that describes heat transfer for flows through heat exchange equipment like shell and tube, heat exchangers, etc. So this is a more appropriate temperature difference to be applying to the Newton's law of cooling for convection. Okay. I will now use the following example to just explain this relationship and demonstrate why it is important in our heat transfer applications. In this example, we are given a steam pipe that flows inside a larger pipe, okay, and this steam then is used to heat up water, cooling water, that is, or cold water, should I say, that is flowing through a smaller pipe. We wish to determine the length of copper tubing or copper pipe that's required to achieve the temperature rise for the cold water. Now, typically, we will generally deal with steady state conditions and therefore also assume that our fluid properties remain more or less constant, and that the conduction of the copper pipe, because the wall is so thin, that the conduction is negligible. Okay, and also remember that the fluid properties that we want to make use of should be determined at the film temperature as shown here. So calculate the average temperature, which is the film temperature, and then determine the properties like Prandtl number, heat capacities, etc. Okay, in this example, we determine that 126 kilowatt of energy is being transferred from one fluid to the next. Note, we don't use the log mean temperature difference here. This is just a simple energy balance, mCp delta T. And from this, we can now move on to calculate the log mean temperature difference as shown here. All right, as well as the heat transfer area, which is 4.78 meters squared, before we go on to calculate the length that is required for this problem, which is 61 meters of copper tubing. Now, what happens if we didn't use the log mean temperature difference? What happens to the length? Okay, so the length decreases by almost half, 36 meter compared to 61 meters. So that is quite a difference. So you can see the effect that or how inaccurate just using a temperature difference is rather than using the log mean temperature difference. In other words, we have under-designed our heat exchanger, which is a big oops in this regard. Okay, you don't want to end up with a heat exchanger at the plant that is half the size that it actually should be to perform the job. Okay. The next few slides should serve more as a recap of work that we have already covered, but also introduce some new information to you that you may need at the moment before this is actually covered at a later stage in a chapter in piping system design, which we'll eventually get to. I understand that you have other assignments that you need to design, things like a biogas reactor, etc. And you might ask the question, how big should my pump be, for example? Okay, so before we get into that, note that we are quite familiar with the Darcy-Weisbach equation. This is introduced again in the heat transfer textbook, but we already go over this in piping systems design, as well as the related correlation for the the friction coefficient F prime. And we have already introduced the following equation for F prime when we are operating under laminar flow conditions. And we also have another form of the Darcy-Weisbach equation, which you should be familiar with, and it has units of meter, and it is very important since this is often used to characterize the performance of pumps at certain flow rates. So we will cover this in fluid movers in the piping systems section of this work. But what is important to note here is just that it is possible to choose or select a pump if you have a desired equivalent height of flow that is known to you. So these pumps, for example, at a flow rate of 0 liter per minute can pump between 12 liter and 23 liter for the left hand side, and between 11 and 20 meter for the right hand side. And these are two different pumps. The one on the left hand side is a normal centrifugal pump. The one on the right hand side is for a submergible pump, where you can actually submerge the pump into the tank. Okay, while the centrifugal pump usually connects it outside of the tank, it has a pipe going to it instead. Okay, so just note the subtle differences here, and note that the higher the flow rate, the lower the pressure, the height difference, the delta P, that can be delivered by that pump. Okay. Also remember that before we came to the Darcy-Weisbach equation, we were first introduced to the Hagen-Poiseuille equation. And this can be used in the case of horizontal pipes only, while the Darcy-Weisbach equation is probably a more appropriate one to use in all our applications, seeing as we are going to have elbows and T's and all sorts, and our pipes are generally not going to operate in the horizontal format. Often in industry I see installations of shell and tube heat exchangers that are in the vertical direction rather than the horizontal. So I would say stick to the Darcy-Weisbach equation. It is a more accurate equation to use because you also introduce the F prime to this equation to factor in for losses and frictional losses. Okay. Flow forced through internal orifices and pipes, etc. Obviously have of course their own specific equations that we would use to determine Nusselt number, depending on whether we are working with a constant temperature gradient and isothermal flows. Now the textbook also provides additional information for these correlations specific to geometries that you might come across. Okay, these are usually the circular one, the pipe, that is the typical one that you would use, but sometimes you would get a rectangular one or ellipsoidal or a isosceles triangle, which I can't say I have seen in industry before. I've seen rectangular shape or square shape and circular shapes, obviously. Okay, the heat transfer textbook also will introduce its own preferred correlations for the friction coefficient. So one example of this is the Petukov equation as shown here. But you may also use the relations that are provided to you in the piping systems textbook. I stick to those. I like the Colebrook. You can use the Churchill if you do a lot of programming, which is much more accurate. But you also see that the difference in the friction coefficient is so small, 0.144, 0.145. Nothing to write home about. So to determine the Nusselt number inside pipes, the following relationship can also be used. It's the Chilton-Colburn relationship, but there's a second one which is more often used, called the Dittus-Bolte equation. The reason why this is used is that it contains this exponential n, okay, which varies depending on whether the fluid in question is being heated or is being cooled down. Okay, so if you're heating the fluid, then use n equal to 0.4. If you are cooling down the fluid, use n equal to 0.3. And just keep tabs of which fluid is being heated and which one is being cooled, because we tend to use we use steam, for example, in industry to heat up fluids. So the steam is being cooled, but the fluid in question is being heated. Okay, so just make sure that you understand which fluid is which and which N should I be using for which fluid. Now, if however there exists very large temperature differences, you can't use these equations. These equations are only for where you have small temperature differences between the fluid and the solid interface. So for a pipe, for example. In the case where you have very large temperature differences, you would have to use the Knielewski's equation instead. Okay, Knielewski. Okay. Now, fortunately, these equations are not that thermally sensitive, so you can apply them irrespective of whether you're dealing with isothermal conditions or constant heat fluxes. And again, as before, there are also specific equations that should be used instead if you're dealing with liquid metals that are molten. So sodium, this is typical if you're dealing with things where you are storing energy, for example. In the past, I know they used sodium mixed with mercury for some applications, an amalgam. So we might still come across amalgams in industry, and then these equations would be preferred. And the Prandtl number here, just pay attention. This Prandtl number should be determined at surface temperatures of the pipe or the conduit in question. To end off the lecture, let us go over a quick example. Water is being heated in this example through 5 tubes. So it enters 5 tubes, and the tubes are maintained at an isothermal temperature of 60 degrees. We also are then asked to determine not only the steady state heat transfer, but also the length of the tubes that are required in this case. Now, we don't know the entry lengths. Okay, it's kind of a catch-22. We first need to determine the length, and then we need to check the entry lengths to make sure that the following assumptions that we are going to make still hold. One of the assumptions that I think I haven't put here is that we have fully developed flow, because we have to then select our equations based on those assumptions, of course. Before we immerse ourselves in the equations, it is often helpful to plan our strategy. So first off, we can calculate the heat flow quite easily for part A, which is then required for solving part B. Now for part B, we need to know what steps need to be taken before we can determine the length of pipe. We first require to know the velocity of the fluid through each of the 5 tubes. Okay, because we have to determine the Reynolds number. So for the next few steps, this is kind of how I tend to think working backwards first is maybe a good thing, because we know what we want. At the end, we want to determine the length required. So for this, I need to determine the area of heat transfer. To determine the area of heat transfer, I need to determine the convective heat transfer coefficient with the Newton's rate equation, obviously. So for part A, I calculate Q, which is then used for the Newton's rate equation, and for this I need the coefficient. So for the convective heat transfer coefficient, I need to determine the Nusselt number, and in order to determine the Nusselt number, I need to first select the right equation, and so I need to know the flow regime, and I need the velocity in order to determine the flow regime. So you can see how I've planned now the different steps that I'll need to take. So first, velocity. So let's get into it. The energy transferred is easily determined using a simple energy balance, mCp delta T, no log mean temperature difference. And we obtain the value of 836 kilowatts that needs to be transferred. For part B, we determine the velocity through each of the pipes. Okay, so we divide by the number of pipes, which is 5. And then we determine the flow regime, which is 57,000. And so since the Reynolds number is greater than 10,000, we have turbulent flow through each of the pipes. I think I mentioned before 4,000. I don't know what I was smoking. It's 10,000. So just correct that. Check your piping systems textbook. The cut-off criteria are available in the textbook for you. So just make sure that you correct for any errors that I might have spoken about in this lecture. Next, we consider two things: the flow regime as well as the temperature difference between the water that is being heated and the temperature of the tubes, which is at 60 degrees isothermal, in order to select the correct Nusselt number equation. So based on this information, we can either use the Chilton-Colburn equation, or we can go with the Dittus-Boelter equation, where the latter, the Dittus-Boelter equation, is obviously a more accurate choice, and so we'll use this instead. We determine the Nusselt number as shown, and we use this to determine the convective heat transfer coefficient, and notice the units here: cabbages per square ox donkey. We also calculate the convective heat transfer coefficient using the Nusselt number, obviously, and we determine it to be 3,700 watt per meter squared Kelvin. Next, we determine the area required for heat transfer, and just remember units. We calculated the heat transferred in kilowatt. Just make sure you use watt instead. And then we ask ourselves a question, very important: should we have used the log mean temperature difference here? What do you think? Okay. And after this, we can determine the length required in total based on the total surface area required for this heat transfer application. You can either do this by determining the total length directly and then dividing by the number of pipes, or else you can determine the area per pipe instead and then the associated length for that pipe. Okay. Use the equation for the internal surface area, which is shown here, and in so doing we calculate the length as 8.24 meter per pipe. Right. The last thing we should do is check the entrance length, that it is not a significant portion of the total length of the pipe required, else we cannot use the equations that apply for fully developed flow. We will have to then look for equations for transitional or developing flow regimes instead. Now let's have a look at that previous question that popped up. Should we have used the log mean temperature difference? Let's see what happens to the final answer if we did this instead. First, calculate the log mean temperature difference as shown as 34 degrees Celsius. Next, determine the heat transfer area, which is 6.66, and then finally determine the length of pipe required and compare the answers. And here we have a difference of 0.24 meters, so 240 millimeter difference. Is that significant? Well, it creates an error of 3%, which is okay, I suppose, but for piping systems design, we already add contingencies, etc. This is avoidable nonetheless. So the error is okay, but I would have preferred to actually use the log mean temperature difference just to be on the safe side. Okay, and with that we end off this lecture with another example, but this time I will leave it up to the student to try it out themselves. So see if you are able to obtain the following answers as shown here. And with that we end off this lecture of forced internal convection. See you guys soon.